My name is Marcus. I'm a software engineer at Prisma for 2.5 years now, and I would like to give you a glimpse of how Prisma works under the hood. So the outline of my talk. First, I would like to look at the history of Prisma. Where are we coming from? Where do we actually want to go to? And this should give you a better understanding of what our technical challenges are. And then, as an example, we will look at how we are tackling that stuff in the case of Photon, the type-safe database client you have seen already in other talks. So in the end, you will have an understanding how to actually, or you will have an idea how to write a connector or implement a connector for Photon. And now you might have, there are 3 reactions to the statement. First one, what the heck is a connector? Second one, why the heck should I care about implementing a connector? And doesn't that sound super complicated? And I will answer those questions in my talk. So, my personal journey. I joined, back then we were still called GraphQL at the beginning of 2017. Who here actually still knows GraphQL? Oh yeah, that's quite a few people. So GraphQL was a backend as a service written in Scala that only ran on MySQL. Over the course of 2017, we learned that our product vision was actually too ambitious to implement for us, and sometimes it was even too limiting for our users. So that's why at the beginning of 2018, we released Prisma, which was basically a reduced free feature set of what GraphQL was doing, and we refined that feature set. So we really tried to extract the valuable components out of GraphQL and put it into a new product called Prisma. Prisma was still implemented in Scala, and over the course of 2018, we added support for Postgres and MongoDB. And also we added the Photon client, which was a predecessor to the Photon client. And at the beginning of 2019, we started to work on Prisma 2, and this time we switched from Scala to Rust because we wanted to have a really snappy and fast experience for our users. So with Prisma 2, we tried to iterate on those codes that we had for Prisma 1, so we wanted to be easy to run and really convenient to use. So this is where we are coming from. Prisma 1 has support for 3 databases, but where do we actually want to go? You've seen this slide in a similar shape in Johannes' talk. So our goal is to be the connecting piece between applications that need to deal with databases, be it in TypeScript, JavaScript, Go. That's what we currently have right now, or later also in Java or other languages. And in the long run, we want to connect to a multitude of data sources. So we again have Postgres, MySQL, MongoDB that we already know, or it could be also Cockroach. We will hear about Cockroach in the next talk, I think. We already heard about Fauna, and we even heard about Stripe. And you may think, oh, on the right side there are 5 databases actually, and Stripe isn't. That's actually not a database. So we want to, in the long run, be able with Prisma to also to connect to any data source. But I will explain that in more detail. And I really love this slide because it looks so easy, and you look at it and you directly have a basic understanding of what's going on. And it contains so much. But now let's pull back the curtain a little bit, and what does it actually mean? So this is a spreadsheet where a colleague did a little research topic to actually look into lots of databases to understand, we want to build a tool set to connect to a vast amount of databases. Yeah, databases are somewhat similar, right? You want to store something, you want to retrieve something, but still, there are lots of databases, and they are different, and they are different for a reason. And we wanted to understand where those differences are. So in the columns in the spreadsheet, we had a look at 21 databases, and we tried to identify capabilities of those databases and where they could actually be different. So we had a look at 21 databases, and in the rows we identified around 80 abilities for those databases. And those green cells mean, okay, it's supported by that database. Red means it's not supported, and yellow means, yeah, it's not supported, but we can probably work around that and create the illusion as if that database would support that capability. And as you can see, there's lots of green stuff, but there's also a ton of red stuff. So databases are just vastly different, although you are using them for very similar purposes. So that sounds a little bit complicated. And not only do we want to connect to any database, right now we always connect to one database at a time. But the reality is where we want to go. So you've heard other colleagues of mine talking about that we often talk to big companies, and they have come up with a pattern. We call that now internally, it's a work in progress title, a virtual database. And so what you have in a company, you have some teams that need to ship some features, and instead of like each team talking to a specific database on their own, they rather connect to a virtual database. Because in big car companies, developers often have a hard time getting access to the data they need. So what those big companies did, here just a few of them, they put a virtual database in front of the actual database, and this virtual database pretends as if all data actually resides in one database. That could, for instance, be handy if you maybe, in this example, maybe you started out your startup on Postgres, but at some point you realized, oh, MongoDB might be a better fit for my use case. But then also some of your data actually is stored in Stripe, and you would have to like have a common API to access all of the data. And this is where we want to go in the long run. So Prisma does not have to only work with any database, it also has to interact with multiple databases at the same time to actually create that illusion of a virtual database. And our products are backed by different engines. So the query engine is a component that is written in Rust that backs Photon. The migration engine backs Lift, what we have seen Tim talking about. Then we have the introspection engine. And in the future, we will also have something that we are currently calling the events engine, which will allow you to like tap into a real-time stream of changes that are happening in your database. And for the rest of the talk, we will do a deep dive into the query engine and how is it currently implemented to actually work towards that idea of a virtual database. So what are the challenges that we are facing here? So obviously, when you use Photon, you expect it to be performant. We want to become a reliable part of any database toolset. So, and we can obviously just achieve that if we offer a performant and scalable solution. But at the same time, you've seen that we want to connect to a vast amount of data sources, not only databases, but also APIs, like for instance, Stripe. So it needs to be easily extendable, otherwise it will just take too long for us to implement co-connectors and actually realize our idea. And in the end, it also has to work with any database. So we have to come up with an abstraction where we actually can assume some parts that are common between all those databases, basically the green cells in the spreadsheet, but still work around the difference in each database. So it should work for any database. It has to be fast. It has to be easy to extend, right? And for any database also means we want to really harness the power of each database. We don't want to give you just like the worst abstraction, basically. And how do we do that? So all our engines are architected in the same way. So we always have a part that is database agnostic. We call that the core. And then we have parts that are custom to each database. This is what we call connectors. So the query engine has its own core and connectors. The migration engine has its own core and connectors. And this is just true for all our engines. And how do you actually split the logic, the responsibilities between the core and the connector, what would you put into the core and what would you actually put into the connector? So a general rule that we have, we try to centralize as much stuff as possible in the core. That means if you put something into a core, some logic, you don't have to re-implement that for a connector. So this is just, if you implement a connector, this is stuff that you get for free. And this is what I try to indicate with that big box for the core. So we try to make it really big and the connectors really small. And examples for some core responsibilities are, for instance, input, validation, and query parsing. So if you do a call to Photon, it will send something to the query engine. This will be parsed by the engine. And for instance, if you then, like all Photon clients currently do the right thing, but it could be that some custom clients suddenly sends a number instead of a string, and this would already catch the error. Then the core can also do some kind of query optimization. So maybe you would write some query that contains some predicates that are not needed, and the query engine core could just filter this out. And the core will also drive a part of the query execution, and this is what we will look into deeper in the coming slides. And what the core can also do over time, so observability and constraints, this is what we currently do not have yet, but observability means basically that the core can emit metrics to any system that we can imagine, so that we can build powerful query analytics solutions on top. So if you, for instance, imagine you have a legacy system in our company, lots of us deal with business issues, and you want to actually have some query analytics for your legacy system. You build a connector for it, and when we have shipped query analytics, you will get some basic analytics for your API out of the box without you having to do anything. So we really try to constrain connectors that they just do simple things. They create database-specific queries, they send them to the database, and they hand the result back to the core. So, and how much code do we currently have in the core versus in the connector? Currently in the core, we have twice as much code as in the connector. This is true for our Scala and Rust version, but over time, we will add more code there. So how does a connector fit into the overall picture with Photon? So as I said, Photon talks to the query engine, which then a request is accepted by the core, which then calls out to the connector to do specific interactions with the database. How is the Photon client actually generated? The core exposes something that we call currently the schema description. So this knows about everything in your Prisma, what do you call it, project definition file. So it would, for instance, say, here's a create post. You can also update the post, and these are the parameters that are needed. Those are the required ones. These are the optional ones. And so this schema description is then used by various generators. Currently, we have one for Go, TypeScript, and JavaScript. So these are all own implementation, and they just use it to actually generate the Photon client. So if there's an operation, create post, it will know, oh, so I need to render a Photon client that allows to call photon.createPost. So that's already nice. This is a lot of stuff that you get for free. But additionally, what I haven't mentioned yet, also in the code sizes, the core also ships with what we call the connector test kit. So if you would implement your own connector, actually, you would be able to run an extensive integration test suite against your connector implementation to directly understand where it's right and where it's wrong and which features you haven't implemented correctly. And this test suite right now contains around 1,000 integration test cases. And so if you take that into the account regarding the code sizes, I think the ratio becomes like 15:1. So that's an awful lot of tests that you do not actually have to write for your connector. And why do we want to do that? You may have noticed that I spoke a few times about you implementing your connector. Why do we want to do that? Because the reason is that we actually want to create a connector ecosystem. So we think not only us should be able to write a core connector, but anyone should be able to write to implement a core connector. So on the top, we have some connectors that are written in Rust, and the ones that we are currently aspiring to ship with our GA, so MySQL, Postgres, and MongoDB. But then there might be also connectors for other data sources. And not all, like we chose Rust as our language, but that might not be the right tool for all other people wanting to write connectors. So as an example, what we always think about is Stripe. So when you use Stripe, it's a very, very handy product, but what happens then is like some of your data is stored in your database, and some of your data, for instance, about orders of your customers or subscriptions is then stored in Stripe. And it would be nice to have like a common facade to talk to that data. So Stripe might be a company that would want to write a custom connector. They are totally into Ruby, so they will probably choose Ruby again. And we want our core to be able to not only call out to connectors that are written in Rust, but also Ruby. And one technology we are excited about here is WebAssembly. So we want to ship a core that is able to talk to any connector that is exposed as WebAssembly. But it could be also that we want to like extend that to gRPC, and you could, as I said, like build your own connector for your custom data source in your company if you really want to strive to build that virtual database abstraction. So what Photon then becomes is basically it's someone like a database abstraction with plugins where you are supposed to, or like you are empowered to write plugins to connect to custom data sources if you want to. So like looking at our challenge slide again, so the core connector pattern is what gives us the power to connect to any database. So the core connector pattern allows us to really centralize that database agnostic logic there. And now let's actually walk as a last thing, as an example, through the query execution of this example Photon call. So on the left-hand side, we have a single Photon call, and on the right-hand side, we have the data model that is behind that Photon call. So we have a blog, and the blog can have many posts, and the post has a many-to-many relation to category, and the post can have many comments. And on the left-hand side, we have the Photon call. So we try to find a block where the name is Marcus block. And then the include syntax here means that we will expand the relation. So we also want to get the related post. And additionally, we also want to get the comments for those posts and the categories. So how would we go about that? How is the interaction between core and connector in that case? So what we could do is that we deserialize that whole call into a query AST, so it would tell you we need to find a block and those posts and those comments, and we would pass on a big data structure to the connector. So it would just call the connector with connector.getRecords and pass in an AST. By the way, this is pseudocode. I chose JavaScript because it's easier to read. I didn't want to teach you Rust today, so just so that is like roughly how it looks like, but not exactly. And you could come up, if you implement a SQL core connector, with something like this. Yeah. Who here thinks this looks easy? Yeah, I'm also not looking forward to write such a query. I don't even think this is right. I just wanted to make an example. So I think this would be a pretty bad example how to implement the interaction between core and connector. So that's definitely not easy to implement. And then that's also the question, is it actually performant? Because that was also a goal we have. So databases are really damn smart, but at some point, if your queries get really complex, databases have something called optimization fences, and then they cannot optimize further because your query is in a shape where they just say, come on, that's too complicated, rather refactor your query. So I'm not saying it's not performant, but it really depends on your use case, and you need to look into it on a case-by-case basis. So this is not what we do. What do we do instead? Instead, we break down the query into smaller chunks that are easier to implement and easier to reason about. So we don't process the query all at once, but we go in small steps. So we will just start out by finding actually the block where the name is Marcus block. So what will happen then? On our connector, we will call something get single record. We will pass in the metadata for our block, and we will pass in our parameters. So the block model parameter, this basically comes from your project definition file, and it contains all the data you might need. You know about the field names, about the types of the fields, so you know what is probably like, for instance, the column types in the database. So all of that you need to actually make a query. And then what does a connector do? Select star from blocks where name equals Marcus block. I mean, that looks a lot simpler, right? This is something I can understand. How do we go on then? Next thing, we will try to find the posts that are related to the block. Again, we call our connector. This time we call a different function. We call it get related records. And this time we pass in the field. So the field on our block is called post. So we pass it in. That contains all the information you might need to do that query about that relation. And then we take our block record, get out the ID, and pass it on to the connector. And what does the connector do? Okay, I'm going to do a select star again from post, where ID, and then the ID that was returned was, in that case, block 1, and we get the post. So we have already fetched the block, we have fetched the post, and now we go into the last step. Now we also need to fetch the comments and the categories. So we need to expand on 2 relation fields at once. So we call the same function again that we called in the previous step, get related records, and we pass in the relation fields again. As those things are independent, we are doing those calls in parallel, so you don't have to do that optimization yourself. And then we pass in the IDs of the post records that we fetched in the previous step. So in that case, if we found multiple posts for a given block, we will pass in all those post IDs. And how do those queries look like? So at first, let's look at the categories. In that case, the query looks a little bit more complicated. In case you remember, the relation between post and category was a many-to-many relation. And how do you implement those relations? Usually in a SQL connector, you have a relation table. So we first need to join on the relation table, and then filter on the categories that are actually related to the post 1, 2, and 3. So, okay, you kind of get this pattern now. Now let's look at the last query for the comments. Now that looks a bit different. Does anybody have an idea what we are looking at here? Yeah, I spared you actually one important detail about what we are working against. I showed you the data model for this application, but what I didn't tell you, only the block, post, and category are stored in Postgres, and the comment is actually stored in FaunaDB. So we just heard Evan talking about FaunaDB, so you launched a new block platform, you're just super successful, you're all over on Hacker News, product news, even TV is talking about you, and suddenly you have a scaling problem. And you remember, at PrismaDay, Evan talked about something, scalable databases, I should try out Fauna. And then, like, as your comment section is the hottest thing on your whole site, you decided to put in the comments into FaunaDB. And what I wanted to show was that it doesn't only get simpler to implement the connector if we go step by step and we just like, give me that block, give me that post, give me that category, give me that comment. We always just try to fetch one type of record that gets easier to implement, but that also makes that virtual database pattern, you know, like connecting to multiple data sources at the same time, actually possible. So recapping the challenges, we already learned about the core connector pattern to actually be able to abstract over the databases in the first place. Then extensibility, so we have a connector test kit. If you want to implement a custom connector for your data source of choice, like the connector test kit will be a huge help. We break down the query execution into small steps so it's easy to implement and that we actually can talk to multiple databases. And as I said earlier, like query batching wise, so query batching means, if we go back, what you see here, we fetch some posts and then we do not iterate over the post to get all, for instance, related comments and doing a database query per post. Instead, like we batch that up and we pass in all IDs of all post records to allow you actually to work with this, in case of SQL, with the in statement that you can get all data at once to avoid the n+1 problem in case you've heard of it. So we try to batch that for performance reasons. Yeah, that's my talk. And if you like to work on this kind of stuff and this sounds like an interesting challenge to you, we are hiring. I mentioned that we are currently our engines are written in Rust, but we are also working in TypeScript, but it's not a requirement that you know any of those languages. If you just like are really passionate about those things and are an eager learner, come talk to us. And questions I will take during the barbecue over a beer. Thank you.